Welcome to Cookie's Maths and Science Hub. Today we're looking at the idea of relative atomic mass. So, what do we mean when we say relative atomic mass? The relative atomic mass given in the periodic table entries, where it's most commonly found, are calculated for all naturally occurring isotopes of each element. Remembering isotopes are the different types of the same element with differing masses. Then, this is based on the abundance of each of those isotopes on Earth. It's also called the atomic weight on the periodic table from time to time. What this means in practice is that on Earth, there is a multitude of different isotopes of the same elements. For example, carbon is one of the most common ones we talk about. Carbon-12 is the most common form of carbon. 98.9% of all carbon is carbon-12. However, there is a small percentage that is carbon-13, 1.1%, and then a tiny percentage that is carbon-14, 0.0001%, give or take. What this means is, when we're finding the relative atomic mass, that is, the relevant mass given all the different isotopes of carbon, we need to take into account each of these isotopes. Given that 98.9% is carbon-12, therefore, our average mass is really close to that 12 because that is what most of the mass of the isotopes is. So in this case, it averages out to be 12.01. So, as those are our three different isotopes of carbon, we take the averages of each of those based on their abundances, and therefore we get the relative atomic mass of 12.01. A method of finding the mass of each isotope is called mass spectroscopy. This involves the ionization of substances and then separating them using a magnetic field based on their charges. This then generates a spectra which can be analyzed to determine the isotopic composition of different elements. And it allows us to see the relevant masses of differing isotopes. We'll go into more detail about mass spectroscopy and how it operates in a separate video, but for now I just want to draw your attention to the spectra it produces. Here you can see each element of carbon, each isotope of carbon that is, and its relative abundance, as well as what mass it has down the bottom. Now this is important as sometimes in questions, especially in those year 11, 12 years, you'll have to calculate the relative atomic mass of a produced spectra from a mass spectroscopy. Let's have a look now at the calculations and how exactly we calculate the relative atomic mass from a known abundance and mass. So the math isn't that complicated, and we can actually find the relative atomic mass quite easily from the abundance and the mass of each abundance. That is, relative atomic mass, or RAM as it is often shortened to, is equal to the calculation shown here, where the uppercase letters are the abundance multiplied by the mass of each isotope. So say an isotope has an abundance of 50% and it has a mass of 50 grams per mole, therefore it's just going to be 50 times 50 plus the different isotopes all over 100. To calculate that percentage part. Looking at an actual example now, in this case we know that lithium has two naturally occurring isotopes, lithium-6 with 7% abundance and lithium-7, 93% abundance. And we're asked to calculate the relative atomic mass of lithium. So looking at our formula, RAM is equal to the formula given over 100. So therefore it's equal to 7 times 6, as we have 7% of our lithium-6 isotope, plus 93 times 7, as we have 93% of our lithium-7 isotope. All divided by 100 gives us 6.93. Therefore, the relative atomic mass of lithium is 6.93 units. Now, we say units as there is no specific unit for relative atomic mass in these examples. What we need to be careful of, and a good way to check your answer, is we can see here that 93% is lithium-7. This means our answer should obviously be much closer to 7 and gives us a bit of an indication of what that number will equal. As our number equals 6.93, we are quite close to that 7 and we know we're on the right track. For this second example, we're asked to consider the mass spectroscopy below. Now you can see here we actually don't know the atomic mass of one of the isotopes, and we're going to have to work backwards in this question because we're given the relative atomic mass just below. If the relative atomic mass of antimony is 121.8 units, find the atomic mass of the isotope with 40.8% abundance. Okay, it sounds a bit more complicated, but let's just write out our formula and plug in our values and see how we go. So we have our formula, RAM is equal to the different variables over 100. So we know our RAM, or our relative atomic mass, is 121.8, and that is going to equal 59.2 multiplied by 120.9, as that is the percentage abundance multiplied by the mass of our isotope that we know, the left-hand one in our graph, plus 40.8, our known abundance, multiplied by X, our unknown mass of that other isotope. What we're going to then do is we can divide the 100 into those two parts. So we can divide 40.8 by 100, giving us 0.408. And we can multiply out 59.2 times 120.9 and then divide that by 100. So we end up with 121.8 equals 71.57 plus 0.408x. Then we just take across the 71.57. Remember, we subtract it from the right-hand side. Whatever we do to the right, we must do to the left in solving algebra. So we get 50.23 equals 0.408x. Then we just divide both sides by 0.408, which leaves us with x is equal to 123.11 units for this question. Now, you'll note here that you can always chuck this back into your equation and check that it does come out to that 121.8 relative atomic mass. Thanks for watching. Hopefully now you have a clear idea of what is meant by relative atomic mass and how to calculate it in simple calculations and solve for unknowns using the formula. Be sure to like and comment on this video with any further ideas you'd like us to cover, and share and subscribe to the channel for future Cookies Maths and Science Hub content. Hope to see you back again soon.